I have to admit I was screaming when I got this video thing.
What makes a marine biologist scream? Roger Hanlon captured this about 10 years ago. He was doing a study in the Caribbean and he'd been following this octopus for about an hour. When it crept behind the rock and went into camouflage mode, he
jammed the camera down right in its face, so to speak,
prompting it to go from camouflage to a startle defense.
Blanching white very quickly.
And then inking him.
But I followed the animal and finished the dive, and I popped at the surface. It was only about 5 feet deep, and I screamed bloody murder, and they thought I was having a dive accident.
When actually he was having...
It was a eureka moment, there's no doubt about it.
And that's because Hanlon is trying to understand just how camouflage works in cephalopods.
Yes, cephalopods, squid, octopus, and cuttlefish.
They are masters of optical illusion.
They are the animals best known to go anywhere in camouflage. No animal comes even close to the speed and diversity of appearances of this animal.
And they have a few tricks at their disposal. Octopus and cuttlefish can change their skin texture.
This is the only animal group we know of that has fine control of its skin to create the bumpiness.
And they match their skin dimensionality by sight, not by touch, which is a
vexing visual perception question.
And of course, they change color. So here's an octopus
doing what we call the moving rock trick.
I'm a rock, I'm a rock. Now watch this.
So the amazing thing is that these animals are colorblind, yet they are capable of creating color-matched patterns. But we don't know how.
But of course Hanlon would like to. And one way he's studying this is by looking closely at squid skin. That's what you're seeing here.
These are super close-up images of live, unanesthetized squid.
And those dots of pigment are called chromatophores. They come in 3 colors.
Yellow, red, and brown. But there are reflectors under the pigments, and the reflectors produce the short wavelengths, the blues and the greens.
And as you can see, the chromatophores can change shape to change the predominant skin color.
Each one of those little spots on there can expand up to 15 times its diameter.
And these chromatophores seem to be twitching all the time.
They camouflage all night long. They don't sleep as far as we know.
That's because cephalopods, with their squishy bodies, rely on camouflage as their main protection from predators. But of course, camouflage is not just color, it's also pattern. This is one of Hanlon's major hypotheses.
We found only 3 to 4 basic pattern templates that they use to achieve all this camouflage.
So there's uniform.
By uniform, we mean that there's little or no contrast in the pattern.
There's mottle.
Mottle is small-scale light and dark splotches.
And disruptive, and the idea there is
to interfere with the recognition of what the animal is.
Based on lab studies, Hanlon says that the animals flash particular patterns based on a few visual cues they encounter in the environment. Hanlon wouldn't call it a reflex because so much visual analysis is involved.
But it is very fast.
The palette and pattern changing in less than a second. But just why these patterns work is still kind of a mystery. Let's take the octopus video again. Hanlon analyzed this video frame by frame, but he can't tell you why you don't see the animal.
We can't find any true statistical matches, whether it's brightness, color, between the animal and the background. So camouflage is not looking exactly like the background.
Camouflage just means fooling whatever's looking at you, which suggests
we're behind the 8 ball, as it were, if we think the world looks like how we see it. There's much more information there, and other animals see it very differently.
For Science Friday, I'm Flora Lichtman.